Okay, so this is part 2 of our video, and in the last video we finished going over example number 3. So now we're going to start a little bit more of a detailed discussion on stress and strain. So we've talked a little bit about stress and how it's measured typically as some type of force per unit area. And we also know that stress can be caused by moment or by torque, right? So we have different types of stress. We have normal stress and we have shear stress, okay? But generally, what we see is that stress is a measure that's associated with the strength of a material that a body is made out of. So this class is called mechanics of materials. In some other places, it's called strength of materials. So you can see that stress is a huge component of the strength of any material. So that's why in this class we're going to be talking about stress and strain, but we're going to be talking about it in the context of different types of materials that we would use in engineering applications. For example, timber or steel or concrete are all going to behave differently when subject to forces that cause internal stresses. Okay. The next item is strain. So still important, probably not as important as stress, but still very important. Strain is a measure of deformation. So we're going to go into a lot more detail on stress and strain, but generally what we know is, I'm going to draw a little picture here. Let's say I have a bar, okay, and I'm going to tug on the bar. I'm going to put this bar in tension, right? So I have axial load on the bar. This should be a little familiar from statics. Like this could be a truss element that is subjected to axial load. Let's say I have some force F pulling this bar in tension. Okay, if I have this, or actually I'm going to make this a cantilever here, I'm going to fix it at one end so it's super easy to see what's happening here, just with one dimension being elongated. So I'm pulling on this bar. What's going to happen? It's going to elongate a little bit, right? So the new length of my bar might be up until this point here. So I have some delta. If this was my original length of the bar, L, I have some delta L when I pull, right? So the strain is going to be delta L over L original. That's basically what I'm measuring when I'm talking about strain. So deformation of a system. Okay, we're going to start with stress, then we're going to move on to strain, and that'll kind of conclude this topic. Okay, so we need to first go over some assumptions before we can jump into solving problems. Okay. So our first assumption is the material in the structural system that we're dealing with, or any system we're dealing with, is continuous. What does that mean? It means it's uniformly distributed and we don't have any voids. Okay. The next assumption we're going to make is that the material is cohesive. So it means that everything is connected together, no cracking, breaks, or separation. Okay. Now we know in the real world this isn't 100% true all the time. Concrete can exhibit cracks. It doesn't mean that the structural integrity of the member has been compromised. So we actually have a way of dealing with cracks, and we're going to talk about that in the very later, or almost like the last 2 topics of this class. But for now, we're only going to be dealing with systems that don't experience any of these any loss of structural integrity in the form of cracks, separations, or portions that aren't connected. So we're going to assume that they stay cohesive. Okay. Now what we're going to do is let's isolate a teeny tiny differential area from this larger area here. Okay. So if we want to isolate some small area of the material, what we see here is we see all of these forces contributing to internal stress. So here we have this first diagram which shows the force, and on the second diagram we're showing how each little element is subjected to, we have our normal stress, sigma y, we have our shear stress in different directions, we have our normal stress, sigma x here, and we have our other 2 shear stresses in the other directions here, depending on how you're looking at this element. So all of these forces, they contribute to a resultant force. These forces then, if we look internally in the system and open it up, are contributing to stresses. Okay, as delta A becomes smaller, so whenever we're isolating differential elements, we want to look at these limits, and what happens is when we look at a limit, you want to think of taking an integral, right? So as delta A becomes smaller, as we decrease this little area that we're looking at, so does delta F and its components in each of the X, Y, and Z directions. So since we know stress is defined as the force per unit area, right? This describes the intensity of the internal force acting on a specific plane passing through a point. And then basically our delta A gets smaller and our stress approaches some finite limit. Okay. Now, normal and shear stress. So our normal stress is the intensity of the force acting normal to delta A. This is sigma. So you guys need to start becoming really comfortable with these notations, these Greek letters that represent different kinds of stresses. So sometimes I'll say sigma, sometimes I'll say normal stress. Those are interchangeable, right? We've talked about this already. If the normal stress is pulling, right, this corresponds to tension. If it's pushing, this corresponds to compression. So here I have a bar and I'm pulling on the bar. This is tension. Here I have a bar and I'm pushing on the bar. This is compression. Okay. My shear stress is the intensity of the force acting tangent to the area, right? So here you can see this is tangent to this plane, tangent to the plane. Whereas the normal here, it's kind of hard to see, but it's coming out of the page. It's coming out of the page in that third dimension. Okay. And of course here, this is also important. This Greek letter is called tau. So sometimes I'll call this shear stress, sometimes I'll call it tau, and maybe even on an exam, I'll tell you to find tau or I'll tell you to find shear stress, and you need to be able to go back and forth between the Greek letter and the definition of that Greek letter. Okay, so tau or shear stress are interchangeable, right? Okay, so again, going back to what we were talking about, this is going to approach some limit, some finite limit, right? Okay, so here what we had before is we have our delta F is equal to sigma delta A, right? Force divided by area. Okay, the sum of the forces acting along the whole cross section must be equivalent to the internal resultant force P at the section. So what happens is, if we're going to let now delta A become dA, delta F become dF, right? And our sigma is constant throughout the cross section. And we know that all the sum, this is from statics, right? The sum of all of those forces has to be equal to the sum of all, the resultant has to be equal to sum of all the forces there. So I'm showing you for the z direction here. We're going to take the integral of dF, equal it to the integral of the area. So this is a dx dy of sigma dA. And we end up getting P equals sigma A. Sigma equals P over A. This is exactly what we had previously defined when we were talking about the man standing on top of a board of nails with another man in between, right? We had said stress is force per unit area. So this is just how we ended up getting that by isolating a differential element, right? So a couple of things here. Let me see if I write it down for you guys later. No, I don't. So I'll write it down here. Okay. Sigma is my average normal stress at any point on the cross-sectional area. So any point I cut that on the cross-sectional area. Okay. P is the same thing as F. I had written this as F over A. Okay, you'll see the P written as P, you'll see the force written as P, which is kind of like a point load. You'll also see it written as F. So make sure you know P and F are the same thing. They just represent a force. This is just saying stress is force over area. Okay, whether you call it P or F, it's the same thing. You'll see the book use P, and you'll see other resources using P or F. So P is this is very important, internal. I'm going to write this in red and in big letters. And I'm going to underline it because it is not your external forces. It has nothing to do with the external forces acting on your system. Remember this. This is how I always remember this. Stress, in colloquial terms, in the real world when we're talking about stress, not mathematically, it's something you feel inside, right? It's something you feel internally. Other people might not be able to see it. It's an internal feeling. So when you want to mathematically calculate stress, you need the internal force, not the external force. Okay? So internal resultant normal force. Okay, that acts through the centroid of the cross-sectional area where you want to find the stress. So you can think about this. If I have a beam that's subject to, let's say, some loading, let's just say 10 pounds, it's simply supported. I hope you guys can all see the stress changes at different points. Let's say this beam has a rectangular cross section like this. Let's say it looks like this. I want to show you guys the difference of what we mean. It's constant throughout the cross section, which means any place I make a cut, you'll see the square. The stress is constant along the cross section at any point. It is not constant at every point along the length of the beam. The stress changes depending on which point you're looking at because the internal load changes, right? Okay, so internal resultant normal force, okay? And A is the cross-sectional area where you want the stress at, right? It's a cross-sectional area at the point where you want to determine stress, okay? Now, it's not the only application of normal stress, but the first application of normal stress that we're going to go over is an axially loaded bar, okay? So I've been talking a lot about beams. We're going to get to beams a little bit later, but this is probably a good time to give you a little bit of a refresher on the different types of structural members that we have, okay? So everybody here has taken statics already, and in statics, you should have talked a little bit about beams, columns, frames, trusses, and had some type of familiarity with those different structural elements, right? Or different structural systems. So a beam, I've mentioned this a couple times now, is generally defined, or is defined as a long, slender member that is loaded perpendicular to its longitudinal axis. So you can see here, the longitudinal axis is this axis right here, right? And it's loaded perpendicular to that. So we're typically talking about gravity loads. These are loads due to gravity. You can think of beams in a building. So if you walk into a parking garage, you look up, you'll see a lot of concrete beams holding up the floor above or the roof above. Those are beams, and they're typically holding gravity loads, okay? This is different. So this is a beam. This is different than a column, right? Each structural element has a different purpose. Think of a column holding up the floor above it, right? So you have all the beams holding up the slab. Then you have a column which holds up all the beams. So what happens is, if I had a beam here, all of my loads from the beam, and you'll learn more about this in structures, but this is a good preview. So all of the loads from this beam will be transferred to the column in something that looks like this, a point load. Okay, and the column will be pinned, fixed here, whatever, and you'll get some type of reaction. So do you guys see that this system I drew is the same as this system here pretty much? This is just in compression, and this is in tension, but they're both loaded in just one direction, in the y direction. Okay, so columns are equal to, they're the same thing as axially loaded members. Columns are axially loaded members. Okay, we design them to resist axial loading. Depending on the type of column and the material of the column, you'll learn this more in like steel design and concrete design. We also design them for torsion because we have something called lateral torsional buckling, but that's not something we're gonna have to deal with right now. Okay, for now, we're gonna assume our columns behave purely or resisting axial loads primarily. Okay, so they look something like this. A couple of assumptions we're going to make before we jump into solving axially loaded member problems is we're going to assume we have homogeneous material, which means it's the same physical and mechanical properties throughout the entire volume, and that it's isotropic, which means we have the same properties in all directions. Okay? And in terms of stress, in engineering, we're interested in average stress and maximum average stress. So you'll see this a lot. We don't really care about distributions. We want maximums. Okay, we want to know what the highest amount we're going to have to design for is. We don't need to know what the lowest is or everything in between. We want the maximum. A lot of times, though, is we end up taking an average, okay, most of the time to cut cost. But instead of using the maximum for design, we'll use an average number, and then we'll kind of let the code compensate for anything that we've underestimated. Okay, but we're basically going to learn how to do average stress and maximum average stress for these axially loaded members. All right, so application of normal stress in an axially loaded bar. So I already showed you this derivation here, how we got this delta F equals sigma delta A. This is where I went through the integral and showed you basically that we end up with sigma equals P over A, and I told you what sigma, P, and A are. Okay, so I'll leave you with this book image here. I'm not going to write it again. Okay, but here, these two images actually show you the sigma equals P over A for both of these systems, one in tension and one in compression. Okay. Now, let's go ahead and try example 4 now. So we have a bar here, and this bar is axially loaded because it's only loaded in one direction, and that direction of loading is parallel or collinear with the longitudinal axis of the member. So that is a check mark. This is an axially loaded member, okay? And we're given the width of the member, the thickness of the member, and we want to know what the maximum average normal stress in the bar is when it's subjected to the loading shown here. So remember, I'm going to write down my formula here. Sigma is equal to force divided by area, okay? You may be tempted to look at this problem and say, okay, well, I want maximum average normal stress. That's the formula for average normal stress. So I'm going to pick the max load on here, which is 22, and it's just going to be 22 divided by the area. Okay? I want you to either pause this video or take a second to ask yourself why that is wrong. Okay? And what you can remember is the word that I had you write in red, underline 3 times, bold, circle, whatever you need to do, right? We are never plugging external forces into stress equations. They're always internal. We want internal forces to measure stress. So with that, we need to figure out where the internal force is max. Where is the maximum internal force? And it's not going to be necessarily where that external force is applied, okay? You can do this any way you like. I'm going to use a load diagram. It's very straightforward, not as complex as a shear and moment diagram. It's very simple. So all you have to do is plot the load versus X, okay? And we'll start here. So I'm going to say anything in tension is positive, anything in compression is negative. I'm starting at 12 here. Okay, actually, let me show you, before I plot these, let me show you the internal forces. So I'm going to make cuts actually to show you what I'm doing here. If this is point A, and I have 12 kilonewtons at point A, and I make a cut anywhere from A to B before those two 9 kilonewton loads to the left occur, I expose an internal force PAB equals 12 kilonewtons. Okay, just so we know, I can give you some context here. We also expose a shear and a moment, right? But why do I not care about those right now? Because I haven't loaded the bar in that direction. There's 0. I don't have any shear or moment. I haven't loaded the bar in those directions. Okay, and I can't have a moment from an axial load because it passes through the axis I would take moments about, right? So I'm actually just going to go ahead and erase these. They're irrelevant for axially loaded members. I don't care about them. Okay, so I have one internal force. I'm going to continue and solve for the rest of these internal forces by making cuts, and then I'm going to show you the load diagram way. Okay, still point A, but I'm going to cut a little farther now. So I'm going to cut after the two 9 kilonewton loads show up. So I still have the 12 kilonewton. Now what I have is a 9 kilonewton load here, a 9 kilonewton load here. And of course here, I'm gonna have PBC, which is equal to 12 plus 9 going in the opposite direction, so I get 30. Okay, and for the last cut, I can either continue from A or I can now start from D. A little simpler because I'm dealing with less stuff on that side, and I can make the cut anywhere before those two 4 kilonewton loads come into play, and I can say that PCD, I know I have a 22 kilonewton here. This is D, and it just gives me that P is equal to 22 kilonewton. You'll get 22 kilonewtons regardless of which way you go and make the cut. You can continue, make the cut A, B, and then pass C. You'll see that you'll get 30 minus that 8, which will give you the 22, or you can do it the way I did it. Both ways will give you the same exact thing. All we need to know is that we considered all of the internal forces. So we have the force from A to B, we have the internal force from B to C, and we have the internal force from C to D. I'm going to highlight those with the corresponding colors so you guys can see that we accounted for everything here. Okay, now I'm going to go and show you the load diagram. Oh, by the way, I think you guys could already see this, but this is my max right here. Right, my max internal load, 30 is larger than 12 and 22, so this is my max. I'm going to show you now what this looks like plotted. So we would start at 12 kilonewtons, it's pulling, so this is tension. Okay, then we increase this by 18 and we get to 22. No change until we get minus 8 here. Oh, I'm sorry, that I counted wrong. This is 30, right? 30. Minus the 8, now we're at 22. And then now we're back down by 22. So either way you do it, here you'll see our max load is this 30, which occurs between B and C. Okay. So max force, internal force. Okay. So now what I'm going to do is say that this is my sigma BC, which is equal to 30 divided by the cross-sectional area. The thickness was given and the width was given, and I get 85.7 megapascals. Okay. All right, so let's try another example here. We have a lamp that is supported by 2 rods, AB and BC. Okay. If AB has a diameter of 10 and BC has a diameter of 8, determine the average normal stress in each rod. So basically what's happening here is this is 90% a statics problem. Okay, this is 10% mechanics of materials, and the only part that's mechanics of materials is you have to plug in just 2 equations for sigma equals force divided by area. So it's the mechanics of materials part is really simple. Okay, you just have to make sure you have the statics down for this. So first thing I'm going to do, I'm going to draw my X and Y axes here. And then I'm going to go ahead and put both of these force vectors into components. Now, I'm just going to do a scalar analysis here. It's pretty straightforward for a 2D system. I'm going to call this force here FBC. I'm going to call this force here FBA. And actually, I'm going to probably use a different color here. Okay, so here I have FBC times 4/5, the adjacent. Here I have FBC times 3/5, the opposite. And here I have FBA cos 60 and FBA sine 60. Okay. So to get the axial force in each rod, I first need to know what the force in each rod is. I'm sorry, to get the axial normal stress in each rod, I first need to know what the axial force in each rod is. So I need to solve for FBA and for FBC. So what I can do, I already drew my free body diagram here. I'm just going to sum the forces in the x direction and set them to 0. The right direction is what I'm defining as positive. So I have FBC times the 4/5 component minus FBA times cosine 60. That's one equation. And I can sum forces in the y. Up is positive. And I can get FBC times the 3/5 component plus FBA sine 60 equals 0. I get FBC equals 395.2. Oh, I forgot the weight. Oops, I forgot the weight here on this free body. I just realized that. I also need to add in W. 80 times 9.81, which is 784.4. Can't forget that. Okay, that needs to go right here. Minus 784.4. Now I can solve FBC equals 392.5. FBA equals 632.4. This is newtons, not kilonewtons. These are all in newtons. Okay. All right, now we can plug directly into sigma BC. So this is the normal stress in rod BC, which is equal to the force in BC divided by the area of BC. So I have 395.2 divided by pi r squared, the area of a circle, and I get 7.86 megapascals. And I can do sigma BA equals FBA divided by ABA, and I get 632.4 divided by pi times 0.005 squared, and I get 8.05 MPa. These are my answers here. And this shows you, this picture here shows you basically what's happening. So I have 8.05 megapascals corresponding to the 632.4 Newton load, right? So that load, that force and tension corresponds to stress distribution that you can see at the cross section of that member here. Okay. All right, so let's try another one of these examples. I have member AC subjected to a vertical force of 3 kilonewtons at some distance x, right? And I want to know what the position x of this force is so that the average compressive stress at the smooth support C is equal to the average tensile stress in the tie rod at AB, okay? They're giving us the information that we need, which is the cross-sectional area and the contact area, okay? Before we jump into this problem, the first thing we need to do, actually before we jump into any problem, we need to first understand the mechanics behind what's happening, the statics behind what's happening, okay? So I'm going to zoom in on this picture and forget everything else for a second here. Right now what's happening is this. I have a smooth support here, so that's telling me that I have some type of roller system here that is not at C, that is not allowing movement in the y direction, okay? And you can imagine if, let's say, this force of 3 kilonewtons is pushing down at some distance x, you guys should all see how that would correspond to compression at C and tension in AB, right? By pushing down on that beam, I'm trying to elongate AB, but I'm trying to shorten whatever's happening at C. Okay, so that should be intuitive before I even start this problem. Now we can refer back to the problem and it's telling us, determine X so that the compressive stress at C, sigma C, is equal to the tensile stress of AB. Okay, so however much I'm pulling in AB is equal to however much I'm pushing down at C. So what is that sweet spot so I get equal tension and compression on both sides? That's what this problem is trying to ask me. Okay, so here what I need to do, the formula would be the force at C divided by AC needs to be equal to the force in AB divided by the area of AB. So the first thing I'm going to do now is I'm going to sum forces in the y direction and moments, and basically I'm doing this because I'm going to apply my equations of equilibrium to see what I can solve for. Okay, let me draw the forces for the free body. So I would have FAB here and I would have FC here. I'm just going to draw these both positive for now. Okay, so if I were to sum forces in the y direction, up is positive, I end up getting FAB plus FC minus 3,000. I'm putting this into newtons, is 0. I can't solve for anything there. And then I'm going to sum my moments about point A, set that equal to 0. Counterclockwise is positive. I get negative 3,000 newtons times my moment arm of X. I don't know where it acts. Plus FC times my moment arm of 200 millimeters equals 0. So what's happening here is I have two equations, but I have three unknowns, FAB, FC, and X. I can't solve for three unknowns with two equations. So I need to now use my third equation here to relate what's going on. And I can say sigma equals FAB over the area of AB, which is given as 400 millimeters squared, which is equal to FC divided by 650. And I relate FC to FAB by just cross multiplying. And now I have three equations and three unknowns. I can plug all three of these in for each other, and I end up getting FAB equals 114.3 newtons, FC equals 1857 newtons, and X is equal to 124 millimeters. So this is the distance required for the tension in the chord AB to be equal to the compression at that smooth support. Okay, so the fun problem, right? Okay, so let's talk a little bit about average shear stress. So how does shear stress develop? Okay, so shear stress, we know, is a stress that develops parallel to the surfaces where the force is being applied. So this picture here, you can see that I have, or in the picture, we have a long member and there is some type of hole beneath the supports. And if we push down with some force F, these sides are experiencing, let me get rid of that. These sides here are experiencing some shear. That resistance to that little block just falling through is a shear force, okay? And what happens is when shear force develops on the side, it corresponds to this shear stress that develops throughout the cross section. A little bit later in a few more topics, we'll talk about that actual distribution of shear stress, but for now, we're just gonna talk about average shear stress, okay? So average shear stress, which means the shear stress across the entire cross section, is just equal to V over A, okay? This isn't the actual mathematical value of the shear at each point on the cross section. This is the average of all of it. To get that actual mathematical value, we're gonna do that in around topic 4 or 5, I believe. So we're not quite there yet. We're just gonna work with the average for now. So our tau average is the shear stress at the section. V is our internal, remember, internal shear force. And A is the area of the cross section at the point we're interested in getting the shear at. Okay. And here I should say this is the internal resultant. This is also important. Internal resultant shear force. This comes in handy, or this is important when we're dealing with things that have multiple forces. We need to make sure we're taking the resultant shear. Okay. Some notes about average shear stress. So the loading case that was shown in an example of is an example of direct or simple shear because the shear on those two sides is caused by a direct action of that load F. Okay, we get this type of shear in a lot of simple connections. Connections are really they're sensitive to shear. So we want to think of things like bolts, pins, welding. Okay, they shear off if we have loaded them too heavily. And that this equation is approximate, remember? So this is not the actual mathematical, theoretical formulation for shear. This is an average approximate value over the entire cross-section. And typically, this equation underestimates our shear. But the reason why we still use it and we still talk about it in some applications is because most of the time, one, shear force doesn't govern, bending does. And you'll kind of understand that concept a little bit more as we go through problems. And then the other reason is this estimate using tau average is only allowed in certain applications that the code says are okay. Okay. Seems like my Apple Pencil is dead, so I'm going to give it a minute to charge, and I'll keep talking about shear for now. Okay. So let's see. Shear stress equilibrium. So what we know is that if we're going to isolate this small element, you can think of this block, this 3D block, coming from a larger beam or some type of element, right? Some type of structural element. If we isolate this small block, what we see here is that all four of those parallel sides are going to be subjected to shear stresses that have equal magnitude, and they're either directed away from each other at the opposite edges or toward each other. So you can see at the top we have our shear stress directed to the right, and then on the side next to it we have it directed up. Those are toward each other, which means that we have equal and opposite reactions, so equal magnitude going down and to the left, okay? This is called the complementary property of shear, and I'll refer to it sometimes when I'm drawing these 3D elements or when we're talking about the shear in different directions, and this definitely comes into play in the later topics as well of this course, okay? So example 7 here, let's see if my pencil has enough juice to write now, okay. We can work with 10%. Okay, so let's start by drawing the free body diagram here. Actually, let's read the problem. Determine the average shear stress in the 20 millimeter diameter pin at A. So they're telling us there's a pin at A, which means it resists translation in the X and Y direction, and in the 30 millimeter diameter pin at B that supports the beam in the figure. So we have two pins here, but we have a two force member connecting that pin to C. So we're going to represent B by one force, that tension in the cable here. I'm going to call this just FB. And then here, it doesn't matter which way you draw this, remember from statics, your equilibrium equations will correct the directions. And then this diagram here shows us the connection, both of these. They're showing us the connections at A and B. We're not going to use those yet. We're going to use those in at the end of the problem, and I'll show you how. Okay, so we're going to kind of put those on the side for now. Okay, the first thing we're going to do is let's try to solve for all these forces and all these reactions. So let's sum our moments about point A, set that equal to 0. This is equations of equilibrium. I have FB, the 4/5 component, which is 6 meters away, minus 30 times 2 meters away, and I can directly solve for FB, which is 12.5 kilonewtons. Okay, guys, the statics part of this has to be as fast as I'm doing it right now. It needs to be very second nature because the problems that we're going to be doing in materials are long. And you need to be able to get this statics info quickly so that you can actually get to the mechanics of materials part of the problem. Okay, how can you get this fast? You keep doing problems. Okay, practice. All right, so now what do we have? What are we looking for? We're looking for the average shear stress in the pin at A and the pin at B, right? Well, we have some forces here. We have the force at B, We have a force in the x and a force in the y for A. So which one do we use? Do we use AX or do we use AY to plug into our shear formula? Okay, I'll write the shear formula up here, right? So tau is equal to V over A. This is what we're looking for here. We use both, right? Because we're taking the resultant. We need the resultant force at A. Which is equal to the V at A is 21.36 kilonewtons. Okay. All right. Now, let's just look at A for a second. So here is A. I know that my force at A, so my V at A is equal to, I just wrote down, what was it? Sorry, my force at A. Let me call it force at A. So I have 21.36 kilonewtons of shear that acts at the pin A, okay? And what happens here is, I can't really zoom in on this anymore, but if we look at the system, I have one force that could be sheared here, or one surface that could be sheared here, and I have a surface that could be sheared there. So I take this force FA, this resultant force, I need to divide it by two shear planes. So really, my V at A is going to be the 21.36 divided by 2, which is 10.68 kilonewtons. So now I can come here and I can say my tau average for point A is VA over AA, which is 10.68. I'm going to convert this to newtons, divided by pi times r squared, and I get 34 megapascals. And now for B, I have 12.5. Let's take a look at the connection. I only have one shear plane, so I don't need to do anything. I only am dividing that over one plane. So my tau average at point B is VB over AB, which is just 12.5 times 10 to the 3, this is in newtons, divided by pi times the radius squared, the area of a circle, right? And these are my answers. I might have a picture here. Yeah, so this here shows you the double shear for A, the pin at A, and the single shear for the pin at B. Okay. Let me see how many more I have of these. Okay, I'm going to stop this video here, and we're going to continue, go on to, actually, let me do this last example so that we'll stop right before design methods. So last example before we're stopping. Okay, so we have a wood joint here with this given, and we want to know what the average shear stress developed along the shear plane AA and BB are, and for each plane, we want to represent the state of stress on an element of the material. Okay. So the first thing we want to do is let's draw that free body diagram of this internal light gray shaded area or system. Okay, and what we have here is, you can imagine if we had this setup here and you're pulling with 6 kilonewtons of force, you see how this plane is blocking the inner light gray member from moving out, right? So what's happening here is, as you're pulling to the right with 6 kilonewton, you get a reaction here, some force reaction that doesn't allow it to move. So our FBD is going to have the 6 kilonewton here, but it's going to have some reactive force that doesn't allow it to move, right? Those are some reactions. And because everything is symmetric here, it's just going to be F. Okay? And you can see if I'm pulling with a 6 kilonewton force, my F has to be 3 kilonewtons on each side. Okay? So that's one thing. The next thing is we want to isolate AA and BB, right? We want to figure out what's happening on those planes. So let's start with section AA. Okay. I know at AA I have that force F of 3 kilonewtons. And then what happens is when I isolate that AA, I'm going to get some shear at A. Okay, and we can see here that my shear at A is equal to the 3 kilonewtons. So now I have the shear at A. Now I can do the same thing with segment BB, which is this bottom segment here. So I'm going to isolate the bottom segment VB, and I have a 3 kilonewton force pushing in this direction. So I can get VB has to be equal to the only force on the system, which is 3 kilonewtons. Okay. Now, since I have VA and VB, all I have to do is plug in my tau average for A equals VA over AA, and that's 3,000 divided by 0.1 times 0.15, and I get 200 kilopascals. And then my tau average for B is VB over AB, which is 3,000 divided by 0.125 times 0.15, and I end up getting 160 kPa. Okay, so that is the last example that we'll do, and in the next video we'll move on to design methods.